hope you're getting some of these or trying some of these optimization problems. A few early ones I think, are pretty straightforward after you sort of work through the anxiety of trying to do a word problem and figuring this out. Um, the next one is a little bit more challenging. It involves a little bit of science knowledge and knowledge of the velocity, distance, time function, so a little bit of physics, and it challenges students, to say the least, so hopefully we're up for the challenge. Let's give this one a shot here. Okay, so in this following situation, I just want to do a couple of corrections here first. Ian and Ada are both training for a marathon. Ian's house is located 20 kilometers north of Ada's house. Okay. At 9 a.m. one Saturday, Ian leaves his house and jogs south at a speed of 8 kilometers per hour. Okay, now this is down on the diagram. Good thing the diagram's given to us. This diagram is shown down here. Okay, right here. So here's Ian's situation. Okay, and he's 20 kilometers and he jogs this way. Okay, and he's approaching, okay, okay, he's approaching, okay, the house here at A. And what's the speed? I think we said 8 kilometers an hour. Good. And so at the same time, so as Ian starts here, at the same time, Ada leaves. And Ada leaves her house and jogs 6 kilometers east. 6 kilometers per hour in an east direction. Okay, so the question's asking, when are Ada and Ian and Ada closest together? And we're going to let this is represented by S. Okay? And it looks like I'm going to have to be closest together. So, okay, this is the distance that they are apart. And this is the one I'm going to minimize. Right? So, Ian's getting closer, okay, to the house. Ada's getting farther away. So before we do this, let's establish a little bit of situation. So at the beginning, at 9 a.m., I'm going to let t equals 0, okay? And Ian would be 20 kilometers away, and Ada would be at 0 kilometers in her trip. Okay, let's do the halfway mark. So t would equal a half. This is just a basis establishing. Okay, so at 9:30, they travel for 1/2 of an hour, and Ian goes at 8 kilometers an hour, right? Ian goes at 8 kilometers an hour. So how far is he from the house? 8 kilometers per hour. He's traveled 4 hours. He started at 20. Minus 4 would be 16, right? So Ian would be 16 kilometers away from the house. Okay, and Ada would be, so she's traveled for half an hour, 6 kilometers per hour. That means she's traveled 3 kilometers in that half hour, and she's 3 kilometers away from the house. Let's do one more here. Okay, let's do one more. Let's say they traveled for 1 hour. So t equals 1. That would be 10 o'clock, right? 10 a.m. on Saturday morning. They've traveled for 1 hour. So Ian now has traveled 8 kilometers per hour. So he's traveled 8. He started at 20 away from the house. He's traveled 8. So he's now at 12 kilometers away from the house. And Ada, okay, travels at a speed of 6 kilometers per hour. And she's traveled for 1 hour. So she is 6 kilometers away. So you start to really quickly maybe understand this a little bit and realize that at any given time, it's this triangle, okay, that they make a shape of. Okay, so okay, I'm going to use the Pythagorean Theorem, and let's figure out this distance. The distance that Ian travels, okay, so this distance here, okay, is always 20 minus, okay, we were doing this type of thing, 8t. So at any given time, he travels 8, and he takes that away from his initial distance. Okay, so this is Ian's distance traveled. Okay, Ada's distance traveled, okay, is a little bit easier. That's 6t. Okay, and that's Ada. Okay, now these happen to be parts of my triangle. So this is 20 minus 8t. Okay, and this distance down here is 6t. Now, if I put this into a formula, I'm going to notice the sides of my triangle I can represent as a function. Okay, so use the Pythagorean theorem. This would be, okay, the hypotenuse squared, that's s at t, and I'm going to take plus 6t. I'm just going to pause this temporarily. I hope this works. I'm just going to pause my video here, let you guys work this out, okay, and we'll get back to you in 1 minute. Okay, so I've worked it. I've expanded the right side of that function, and I've collected like terms. I've worked it out to this situation here. Now I'm going to have to take the derivative. So let's just do one more line here, and I've got and that's the square root. Okay, so now I can take the derivative. I'm going to use the chain rule to take the derivative of this. Okay, fix that correction. And now I have to take the derivative of the inner product here, and that's negative 320 plus 200t. Okay, so I think I've done the chain rule properly here. I brought my 1/2 down in front of my inner function, and then I've knocked the index down to 1/2 to negative 1/2. So I have to have the 1/2 out in front, and then I have, okay, the derivative of my inside function, and that's just negative 320 plus 200t. That 200t came from 2 times 100t. Okay, this is a rational function. Okay, so down below I have 400 minus 300t plus 100t squared, and in the top I have negative 320 plus 200t. Now, since I have to minimize this, that means I have to take the derivative. I've done the derivative, and I have to set the derivative equal to 0. Well, conveniently, this looks like a challenging function, but since it's irrational, that means that the numerator only equals 0. Remember this concept? I hope you remember it, that when I have a fraction and it equals 0, it's the numerator, it's the top of the fraction that equals 0. So my focus can be just on the top of the function. Okay, the top of this function is the only thing I need to worry about. The bottom is, okay, the denominators are very messy. That's all right, that's fine. I should write it as the function, but then do my work here. Now this is just a nice linear equation. Easy to solve. We get t equals 1.6 hours. Okay, so what this means in the context of the question is that the Ian and Ada jog for 1.6 hours. Okay, and that's when they're the closest apart. They actually jog for 2.5 hours, right? So R didn't really consider this earlier. Okay, they jog for 2.5 hours. So somewhere in this time period of 0 to 2.5 hours, sometime they're closest together, and we just found that to be 1.6. Now, in relation to time and clock, just another science thing here. I'm asking what time, okay? Okay, what time, when are they closest together, given that they're both? So let's see what time that is. So 1.6 hours from 9 a.m., okay, is 10 hours and what's 0.6, okay, of an hour? That's 36 minutes. Okay, so at 10:36 a.m., okay, they are closest together. Okay, and I could actually figure that out if I have a value of t and I do 1.6. I could put that that into my little work here that I did in the beginning here, or put it into any one of my functions and find out how much that distance is. That'd be the minimum distance. Okay, I think that's good. You may have to pause that and think about that one for a few minutes and sort of go with that. Let's do one more today, maybe two more if we have time here. Oh, this is a good math one here. Really nice, real quick one here. Okay, just involving numbers, a real number problem here. Okay, so find two positive numbers with a product equal to. Okay, so I'm going to let my two positive numbers, the x and y, are two positive numbers. Okay, so right off the bat, I have my domain restriction here, such that the product is equal to 200. So my product, is going to be x times y, and that's 200. I'm just going to write this as a equation. It's a little bit better. Okay, such that the sum of one number is twice the other, and twice the other is as small as possible. Okay, so my sum function, is one number and twice the other number. Okay, and that's as small as possible. Oh, okay. So this to me looks like my optimal equation because it says as small as possible. That's the one I want to optimize. That's my optimal equation right here. And I'm going to write that, eventually as a function of x. Okay, this one's my constraint equation. Okay, so it's under the following constraint that the product of the two numbers is always equal to 200. So let's solve for y. Okay, that just means division by x. And now I take my 200 over x, which is y, and write it into my optimal equation. So effectively, what I've done here is write a function of x. S as a function of x. So the sum in terms of x would be x plus 400 over x, and we know that to be so do you know what to do next? Take the derivative. Always take the derivative. If you have a function, take the derivative. Okay. Now we take the derivative and we set it equal to 0 because we want the minimum sum. I think it's the minimum. As small sum is as small as possible. Okay, so I take the derivative, set it equal to 0. That means I have to solve for a derivative function. Okay, I can do it like this. I can that would be here. Okay, I'm sorry, let's just erase what I did here. So I've got 1 over, 1. Sorry, I'm messing this up here. Let me just correct this one real quick. You probably saw my mistake here. Okay, so it's 1 equals 1 over 400. 400 over x squared. Okay, that means x squared, if I cross multiply, x equals 20. Okay, so there's my one answer. And if x equals 20, I'm going to use my constraint equation, and y would equal y equals 10. So y equals 10. Okay, and I found my two numbers. They're both positive. They're both greater than 0. The two numbers are 10 and hang of this. The setup is the hardest. Okay, absolutely. The setup, setting it up, understanding the problem, trying to write the equations, maybe use a diagram if it's necessary. Okay, not for this last one, but certainly, okay, understanding it and working through it. I can absolutely give you help with understanding the question and setting up the equations, both the constraint equation and the optimal equation, sort of getting you started. I think the math will be easy once you get it started. And there's always this little check process here. So let's try and do one more. We still got a little bit of time left. I like to try and keep these get down to about 30 minutes. Okay, so let's do this one here. All right, good. We've got a diagram. That's good. Okay, so we've got 2,700 square centimeters. So that's surface area, right? Centimeters squared is surface area, and that's going to be, okay, the outside of the box. It's available to make a box, a square-based box, and an open top. So, okay, no top for it. Find the dimensions of the box that provide the largest volume. Okay, so largest volume is going to be a maximized question. Okay, and I want to write the volume in terms of, okay, a function. Okay, now I've got some things labeled here, x and x and right, x and x and h. Okay, and I'm going to use 2,700. Okay, so I've got my surface area. What's the formula for my surface area? Okay, a surface area is going to be my constraint equation. It's going to be 2,700. And in this particular case, my surface area is, okay, no top on the box, but I've got a bottom, right? I've got a bottom, that's going to be x squared, and I've got four sides, and the four sides dimensions, okay, are 4, and the side is x times h. I've got 4 of them, right? So each of my sides is a dimension of x times h, x times h, x times h, x times h, and that equals 27. Okay, this is my constraint equation. Okay, it's always under this constraint here. Well, let's rearrange this and solve for h. Let's say h is easy to isolate. It's right here, and that means that I can rearrange my equation. Okay, so h would be 2700 minus x squared all over 4x. I'm going to go one step. Okay. Let's divide. Okay. H is, I've got here down. Okay. So 4 into 2700, and there's a 4x into 2700. Okay. So that means I've got, okay. Oh no, let's just do this. Let's just leave this for now. Okay. A little bit. That's good. Right like this here. Okay, let's focus on our volume question when we're going to maximize. We have h in terms of x, and I'm perfectly fine with that for now. Okay, our volume function, okay, is length times width times height. Okay, so as a function of x, okay, our dimensions, okay, our length and our width are our x and our x. Okay, and the height, okay, is we just found in terms of x to be, okay, so that's why I left it. Okay, I was going to work that out, but I realized that it's just as easy to work it out here. So let's do a little bit of math here. Okay, when I bring that in and simplify, let's clean that up. I've got 1/4 x. I'm going to do the 4x into the x squared. Okay, and that leaves me with 2,700 minus x squared. And if I actually do the calculations here, I've got in my notes, I've got 675x, okay, minus 1/4 x to the power of 3. And all I did was distribute that in here. So this is my volume function, okay, in terms of x. All right, we've down to our equation, and that means I take the derivative. Yes, good. Okay, stop there for a second. Just pause that if you want and verify that that's your derivative. And this is the one we make 0. Because I want to find volume. Okay, the maximum volume, right? I have a certain amount of surface area to use to construct this square, but I want to make the biggest box possible, right? With what I have, and it could be different dimensions. Okay, so let's solve this. I like to do it, okay, by moving my terms around, working out it, but I've got, okay, so multiply by 4 divided by 3. So 4 multiplied by 4 divided by 3 is going to give me x squared. When I multiply 675 by 4 and divide it by 3, I get 900. So therefore I get x equals 30. So x equals 30 is my dimensions that are going to give me my maximum volume. Okay? And that would mean that h, okay, I go plug that into this equation would work right here, the constraint equation. So if x equals 30, I think I've got a calculation according to my notes. I'll let you guys figure that out for yourself. That works out to be h equals 30 centimeters. Okay, so our actual maximum volume, I'm just going to do a volume check. Okay, so at 30, what would this volume be? So the volume at 30, I can use this equation right here. That works out to be notes, I've got a volume of 13,500 cubic centimeters for a volume, when h equals 15 centimeters and x, okay, is 30 centimeters. All right, good. That's almost 30 minutes. I think I'm probably going to stop, and you guys can look ahead and do the next one if you want to. That's where I'll pick up my video tomorrow here, the minimize cost. Okay, this one here, very similar to the one we just did, except we have to minimize the cost. We've got a cost factor here, so again, that's very similar to the one we just did. Okay, but we have to incorporate the cost and the different costs for the different sides. Okay, good luck. Keep working on it. Again, like I said, these are challenging. This is a challenging part for kids students in a regular classroom, not kids, students in a regular classroom when I'm there every day to answer questions, explain these to you. So you guys are even having more of a challenging difficulty trying to isolate and learn this on your own. But good luck. Keep working at it and keep asking me questions, especially if you need any help with the optimal and the constraint equations, developing those based on the word problem and maybe the diagram as well too. Good luck. We'll talk again soon. Bye.